Alright, let's just go ahead and get started. I believe that we're looking good. So hello everyone and welcome back to OpenGL. It's been quite a bit, but I needed to take a break, to be honest, just because we grinded the shit out of OpenGL in the summer. Like, holy fuck. But now we're going to kind of switch gears away from collisions, and we're going to go into lighting. Specifically today we're going to look at what Blinn-Phong lighting is. So as of now we implemented the model called just Blinn lighting, or no, not Blinn-Phong lighting. So pretty much everything that one second, let me just turn it down. Hold on, I actually need to make sure that this music is okay. It's looking good. Yeah, so everything that we have here, so the light direction, diffuse, specular, all of that is the Phong lighting. Blinn-Phong lighting is essentially a small extension of Phong lighting in that it fixes one small but crucial error. So let's look at this in one note real quick. So we'll look at what the Phong model does in regards to in terms of calculations, and then we'll see how the Blinn-Phong lighting changes that. So let's say we have our light bulb, or our light. That's on a mushroom. It's a light bulb. Trust me. There you go. Okay. So it produces some light, right? And then we have our, oh shit, that's, or you know what, that actually works actually. I'll do that. So our normal, so this is our, shit, how do we want to say this? This is, we'll call this light, so L. So the light direction. We have our normal vector N. And then let's say we have our I right here, our viewer. Guys, I should become an artist, shouldn't I? So, or you know, let's actually move this down a little bit. Holy crap, this is reminding me of physics. Holy shit. No joke. This is exactly what I drew, a fucking eyeball. Alright, so this is our reflection vector right here. And those thetas are the same. That's just a law of reflection. And then we have our view direction. So this. So in Phong lighting, what happened was it calculated the dot product between V and R. So we took V, which is this, and R, which is right here. We found this, or it didn't really matter what the angle was, but we just found the parallel component. So we returned what this was. And we normalized these vectors as well. So we found what this component was, and this was, what do we call it, spec? Let me just check that real quick. Or what we did was this is the dot product here between the view direction and the reflection direction, and we just did a couple calculations to it, and then raised it to a power, and then we called that our specular, or our calculated specular constant. So yeah. So this is our specular. What do we actually call it? Just spec. Okay. Yeah. So this became the dot product that we use to calculate spec. Now this works for most purposes, like especially if the angle here, so theta 1 was less than 90 degrees. Because the dot product works actually very well, in this case at least. with or wait, what was I saying? The dot product works very well with calculating these constants. However, what if theta is greater than 90 degrees? So you might see something like this. The view direction is all the way over here. So theta over here, or wait, no, not theta. We just call this V2 for a second view direction. And we have a larger theta. I'll actually just erase these. So this is theta 2. That's a shitty normal vector. And what you'll find now is that this, since this view direction is back here, what happens is the specular value is calculated to be negative, because the component that is parallel is essentially, oh wait, no, that's the wrong one, sorry. So we find the component that is parallel to the reflection vector. And in this case, it's negative because we kind of extend the vector, the reflection vector, backwards, and then we just see what it's parallel to. So this component here is a spec less than 0. So this is theta 1, once again, and this is theta 2 greater than 90, and this is less than 90. And even better, if it is 90, you have no specular value. And what we do now is, in the calculation, we say take the maximum of the dot product and 0. So if this value is negative, it just completely nullifies it. So it doesn't even display any color, even though at this view direction you wouldn't get much, but you still would get some. So what Blinn, what's his name? It's all in this article here. Blinn, what's his name? James F. Blinn. So what James did was he used essentially the same model. So Blinn, let's have the same setup. So a light bulb, kind of deformed. Let's have a different surface. And let's look at this point right here. So we have our normal vector. Once again, we have our light direction. So this is light. And this time, we're not going to calculate the reflection vector. Now, the reason why is here. So let's say we had our person, normal stuff. This is you. Oh wait, no, that's almost perfectly on the reflection. Let's have our viewer right here. Oh, that doesn't look like an eye. There, that doesn't even look like it either, but deal with it. So a reflection vector is something like that. Doesn't really matter. Our view, I think we called it a view vector. But that's what this is right here. And that's just from the fragment position to the actual viewing position. And we'd calculate whatever, but once again, that won't work if the angle between, like, let's say we had our viewer right over here. Once again, this will not work. This is kind of a bad example, but you're going to get the gist at some point. So now, instead of calculating this reflection vector, what we do is we calculate something called a halfway vector. So halfway between the light and the view. So this is V2. So halfway vector would be right here. So H2. So H is equal to the halfway vector. And for the regular one, we say H1 is something like that. So now instead of calculating the dot product between the view vector and the normal vector and the reflection vector, what we do is we calculate the dot product between the halfway vector and the normal vector. So we have our normal vector like this. Halfway is half-1 is like that. That essentially continues, and halfway 2 is like this. So the reflection vector would give us a angle greater than 90 for the second halfway vector. However, this theta is now less than 90, so it's going to give us a positive dot product, which is shown right here, and this one gives it over here. So now we have positive lighting on both sides. I think I drew this wrong. No, yeah, this is actually wait a minute. Yeah, this is very wrong. But it should be something like that. Well, either way, you get the gist. So if the angle is greater than 90, you still get some component back to actually display specular lighting. So let's actually jump into the code right now. And just one more thing, the halfway vector is, you can calculate it as the average, I believe, but you can also just say it's the normalized sum. So we're going to say L plus V, and then normalize that, meaning just divide it by let me just say normalize, because I forget what the actual formula is, but like that. Okay. There are much better diagrams on the page that I linked down below. Okay, so let's go into the code, and I did make some changes recently to the code, just naming minor stuff. I put all those on GitHub. There's a commit. The link is down below. So I think it's just like 2 or 3 things, just a couple of naming things here and there, just to make the code a little more readable. Okay, so let's go right into the fragment shader. So object.fs, this is our main fragment shader. The way we're going to show this is we're going to have a switch, essentially. So a uniform Boolean value to tell us whether or not to actually, let me just put the tablet over here, to tell us whether or not to actually display, or which method of lighting to use. So what that's going to look like is a uniform bool, let's call it Blinn, or use Blinn. Now in each method, so in calc dirlight, calc point light, and spotlight, we're going to have to implement this. So let's just start with dirlight, and you can kind of follow suit. So what I'm going to do right now is give me half a second. Okay. Yeah. So at the top of dirlight, I'm gonna move all the directional vector calculations up here. So directional vectors. Oh wait, no, we're actually fine with the way we are. That was a lie. Okay. So for specular, actually, we're going to do one thing. So in specular, after the comment, we're going to create a placeholder. So vec4 specular is equal to vec4 0.0, 0.0, 0.0, and 1.0. Now the reason why we're creating a placeholder is because we might not assign something to it right now. So the place when we wouldn't assign something to it is if diff is greater than 0, we're going to change this to actual lighting values. This is something I didn't catch last time when we actually did this a while back. And if the diffuse lighting is less than 0, what this means is the object is essentially behind the light. or the fragment is behind light because there's a negative or a zero dot product between the light direction and the normal value of, or the normal vector of the fragment. So if that's negative, you could tell it that there wouldn't be any light shown on there. So we're going to say if diff is greater than 0, now we're going to perform our calculations. So we're going to say float dot product is equal to 0, another placeholder. God, I'm stuttering. It's been a bit. So next we're going to say if Blinn, or if use Blinn, sorry. We want to calculate using the Blinn-Phong model, using Blinn-Phong model. So the way we'll say that is we first want to calculate the halfway vector once again. So vec3 halfway dir is equal to normalize light direction plus view direction. And then we want to calculate the dot product. So dot prod is equal to dot of normal and halfway direction. So we're doing that dot product there. Else we're going to calculate using the just the Phong model. So we're going to take the reflection direction, or the reflect direction, put that vector into here, and then we're going to calculate the dot product. So dot prod is equal to dot of view direction and reflection direction, or reflector. And then outside here, what we want to do is outside of the if else statement, we want to move the constant calculation into there, and we're going to still calculate the float spec, but replace the dot function call with dot prod, because we want to pass in the corresponding dot product. And then when we say vec4 specular, just replace that with specular, because we declared that vector outside of the if diff is greater than 0. So we essentially have to do the same thing for the rest of them. I'm just going to add one more comment up here. So if diff is less than or equal to 0, object is behind the light. Okay, so I believe that you can just it's negative light direction normal. Yeah, okay. So yeah, we can do this. So take everything that you did to calculate the specular. So from the placeholder and the if statement, so the specular vector and the if statement, copy that and then go into calc point light and replace the specular calculation with that. So it should look like that, and then do the same thing for the spotlight. Right here, specular. Do not interrupt intensity or anything else there. Keep that as is, but make sure that you're replacing the existing specular calculations. Okay. So pause the video if you just want to take another look at this. So now we actually want to go ahead and implement this. So we want to see how it'll work. So we have this Boolean value here, and how are we going to change it? So we actually have in scene, we have, if you remember, a variable log. So we created that 2 videos or two or three videos ago, I think, but it's been a month. So we essentially, in our scene class, we have this variable log that I use from my JSON library, and it just allows us to store variables of any type without having to type in bool, use blinn, or time, and it stores dynamic types. So the type is, and it maps essentially strings, or it's a JSON container essentially. So it can be whatever you want. hold on, let me write something down real quick. I just thought of something. Union. Alright, sorry. I just came upon a realization, but it won't affect this at all. I misspelled window. Okay. Yeah, so this is our variable log, and we can go into scene.cpp in process input. My mouse, you're hearing my mouse wheel scroll, by the way. Underneath where we set the position, we just want to say, or you know what, in scene.init, underneath where we initialize the free type library, we want to set up the lighting variable. So we're going to say variable log at use Blinn is equal to true. Just like that. And then in process input, so we're using the square brackets here because once again it's a map essentially. So we just use Blinn and then say true. And then now go to process input, and we're going to update Blinn if necessary. So if keyboard key glfw key, and we'll say B. So if that key went down, my mistake. We're going to say variable log at Blinn is equal to variable, or we're going to reverse a boolean, so not variable log at Blinn dot val, and pass in a template argument of bool. So we're essentially getting the value from the JSON container, and then we are reversing it. And then, or this should be use Blinn. And then now in render shader, we want to say if apply lighting, just pass that in. So shader.set bool, the name is going to be use Blinn, and the value will be variable log at use Blinn dot val template argument of bool once again. Let me just make sure this is right. Yeah, all right, that looks good. So let's actually, we'll run this, and you're not going to be able to see it, just because it's going to be, oh wait, I didn't even put a semicolon. Also, you'll notice that I removed or commented out the skybox just for now. So if I do that, and let me try. It's kind of hard to see there because the ball's moving. But let's go ahead and actually create a cube, or let's create some sort of a platform rather. So let's actually go to cube.hpp first, just because I want to make it have a different material. So like red plastic or something. So in cube, so the cube.hpp, and void init, we're going to set the material value. So what we're going to do here is we're going to, since we have to use the async or async, I don't even know how to say it. I never knew how to say it. We're going to create two colors, so AI color 4D diff, and then we're going to initialize it with an RGB value from the material class. So if you remember, however long ago, we created a material class that had a bunch of material data for lighting, a bunch of specular, diffuse, and ambient data, and ambient, I think, yeah. So yeah, it had all this data, and it made, oh shit, that's not right. Yeah, so this is somewhat accurate, so we just have a bunch of choices to choose from. So let's say the diffuse, I should create a function to convert, but for now we'll just pass in each value separately. So for diff, we're going to say material colon, or colon, and let's say red plastic, dot diffuse dot r, and then copy and paste this for G and B, and then put a 1.0 float at the end, and then do the same thing for spec, and then just call material red plastic dot specular dot RGB. Like so, and then we just have to initialize the mesh constructor using diff and spec, and it will automatically initialize the mesh as a material object rather than a textured object. So this cube will now render with the red plastic texture or material. Now to actually create this platform, we can go ahead and create a cube instance. So we'll say underneath where we do all the box or the lamp stuff and the sphere, we can say cube, one maximum of one instance, and then scene.register model, a reference to cube. So this is just the standard procedure that we have to register a model with the scene. Scene.load models does that, and then down here where we actually, before we say init instances, we want to generate this instance. So we're going to say scene.generate instance. Then the ID is going to be cube.id. Size will be glm vec3, and I want to make it let's make it 20 by 20 in the XZ plane. So 20.0 float, and then 0.1 float for the Y, and then 20.0 float. And then the mass will be 100.0, and then position will be glm vec3, 0.0 float, negative 3.0 float, and 0.0 float. And then we just want to render this in the main loop. So where we render the launch objects, just move the scene.render shader, because we're going to use the same shader. So just move that render shader outside of the if statement, because we always want to render it, since we're always rendering the cube or the platform. And then we're going to say scene.render instances, cube.id, shader, and dt. Just like that. And if I'm correct, I hope it renders. Okay, yeah, okay, there you go. See that? Look at that. Looks nice, right? So I have my flashlight. I can turn this on and off. This was also another thing I fixed. There was an error with the method call, but that was also fixed down in the commit, in the small one. So let's press the B key, and you see how it changes a little. So right now we are in Blinn, or just in Phong lighting, and you see how it's a little more dispersed. But let's change it back to B. So Blinn-Phong, and you see how it's more concentrated. So let's get a little closer to the reflection direction. I need to print out actually, because I'm forgetting which one is which. So you don't have to do this if you remember, but I'm just going to go ahead and print out when we use Blinn. So std cout. In the scene class, I'm just going to print out variable log dot at use Blinn dot val boolean. And then alright, so we're currently at 1, and then I go to 0, so you see how it scatters a little more. Or wait, am I thinking of this right? But I mean, you can kind of see how it changes. Like that looks, is that, fuck, which one is it? Yeah, so that is, alright, so yeah, this is the direction light that's coming from up there or whatever. And we are currently on the Blinn-Phong model, because that's what that 1 stands for. You know, let me actually just make sure of this real quick. I'm gonna lose my mind if I don't get this. So, object.fs. Don't worry about this code right now. I'm just making sure I have this right. Okay. Good. Okay, yeah, we're good. Okay. So yeah, you can kind of see the difference here. So if I turn my flashlight off, it is kind of weird because the lights are weirdly spaced out, or I don't know. It might be the material. It's just weird though. Or you know, you can really see the difference if you look here, but it's not strong enough. But yeah, you can kind of see how when, I don't even know if you guys can see that, to be honest. What's up, RKB? Can you see this well? Like, can you see the difference in the lighting here? I think it looks, okay, yeah. All right, I'm looking at the output. Yeah, okay. I think I just have my monitor brightness really low. But yeah, so you see how in just the Phong lighting, the light is a little more scattered. It doesn't look as good. But then when you change it to Blinn-Phong, you see a more like steady stream of the light, and the kind of reflection is more accentuated. So yeah, is that it? Yeah. See, we did something cool there. You can also, once we're done with this, if you want to, you can also remove the use blend here, the if statement here, and just make it always do use blend. And then in, what else was it? I wanted to say something else, but I'm forgetting. Oh yeah, I wanted to brighten up my flashlight because I did want to see how that looked. So 0. Should look a little better. Yeah, so the flashlight was super dim, but here, let me just turn the lights off. Okay. Oh, right, yeah. So yeah, you can kind of see the difference here, especially here. How when you're really close to the normal vector, there's more, or I mean this is just the Phong lighting. How you see that kind of outer ring and it looks like shit. But when you go to, or you see the outer ring in both places, but there's just less light when it should look a lot more like that, especially when the flashlight's pointing directly at the platform. So yeah, it's more accurate in general. So yeah, you can also remove the output too. Oh, what did I just do? All right, I don't know. Yeah, so that was pretty much all I wanted to say, really. I got a Windows update. I can't sleep on that one. Yeah, so pretty quick stream. As for OpenGL, I'm gonna release another video like tonight, I think, on gamma correction, with just some more lighting, and then we'll do some shadows after that, which might be Thursday. I don't know if I learn it or if I have the code ready by then. But yeah, so Yeah, I don't know. And then we'll figure out where to go from there. Or actually, after shadows, we have normal mapping and like depth. Like adding depth to models without like changing the vertex structure, so it'll be like another texture in a way. And then we can incorporate some Perlin noise into that, which will be pretty cool. But yeah, so that's all I wanted to say for right now. Yeah, I'll see you on Thursday or whenever I do shadows. So yeah, until then, have a good one.